Welcome to section 13.1, comparing three or more means. And we compare three or more means by something called a one-way analysis of variance. So to get results about the three means, we actually analyze the variance, which is sigma squared. So we talk about the spread to test the mean. Okay, so we call it an ANOVA. That test is an ANOVA. It's analysis of variance. And so there's a lot of theory that goes behind an ANOVA. So we're going to begin our discussion about why we should do an ANOVA test versus maybe just doing three separate hypothesis tests, something like this. So for instance, comparing each mean pair by pair. All right. So this would be one way to compare three or more means, okay? And the reason why we don't do this, let's say each of these hypothesis tests had an alpha equals 0.05 level of significance. All right, so if we perform this 3 times, well, let's see. So if alpha is 0.05, that means we would, sorry, I'm having issues with my pen, correctly keep the null hypothesis 95% of the time. So we would run a test correctly 95% of the time. And if we use our multiplication rule from chapter 5, we know that we would run a hypothesis correctly and keep the null when we should. 0.95 to the 3rd power, which is 0.857. So that would mean our new alpha is now much bigger than 0.05. It's 0.14, okay? So why are we doing this? This is the motivation about why we're introducing our ANOVA test. Okay, so let's go down to how the hypothesis test is going to look for an ANOVA. Again, we're dealing with 3 or more populations, so this is what our null hypothesis is going to look like. The null is going to be that the first mean is equal to the second, is equal to the third. Okay, and then we could have more populations. For instance, if we had k populations, then we would go up to mu sub k. All right, so there's our null hypothesis. And then our alternative for an ANOVA test is always going to look like this. At least one mean is different. Okay, so there you go. So I wanted to make a note. A common mistake is to write your alternative like this. So our alternative H1 is not stated like this. We do not say mu1 not equal to mu2, not equal to mu3, etc., etc. All right, because that's not what we're saying. So for instance, maybe mu1 and mu2 are equal to each other, but then they're different than mu3. Okay, so then this doesn't hold. And we're just really testing this, that just at least one mean is different. Okay, so let's Now that we know how we're going to set up our ANOVA, our hypothesis test, let's talk about why we talk about the variance when we're trying to find out about the means. Okay, so let's go. So the basic idea in a one-way ANOVA is to determine if the sample data could come from populations with the same mean, or suggest that at least one sample comes from a population whose mean is different from the others. To make this decision, we compare the variability among the sample means, so how different the sample means are, to the variability within each sample, how spread out the sample data is. So we are going to look at that example. We're going to take a simple example and we're going to determine if the sample data could come from populations with the same mean or suggest that at least one population has a different mean. Okay, so consider the data below. So we're gonna consider these two separate hypothesis tests, all right? So the X's, that's gonna be one ANOVA, and then the Y's are totally unrelated to the X's, and that's gonna be another hypothesis test, okay? So we're gonna be looking at two hypothesis tests. And this is what we're going to do, or what we're gonna get from our lesson. So the sample means are the same. The sample means are the same. We can see that right here. These two columns have the same mean. These two columns have the same mean. And these two columns have the same mean. Okay, so remember this part up here, the variability among the sample means. We look at that variability. So that's staying the same in our simple example. And what's going to change in our example is the variability within each sample. Okay, so let's begin with a dot plot, and we'll do the X's up top, and we'll do the Y data sets on the bottom. Let's notate the X's with, we'll do red circles. So X, we have 4, then 5, 2 6s, and a 4. Okay, and then the mean is 5, so we'll put the mean down below. It's at 5. Okay, let's do X2 with blue squares. So we have a 7, 8, whoops, a 9, another 7, and a 9. And that mean is 8, right in the middle. And then finally, let's do some yellow triangles for the X's, X3s I should say. So 2 10s, 2 11s, and a 13. And the mean again is 11. So there you go. So looking within each sample, all right, so that's one sample. The blue is a second, and the yellow triangles is a third. There's not a lot of variability within the sample. They're all pretty much hovering around the mean, okay? So the variability within each sample of X is small. It's all pretty close to the same value. Let's repeat the same process with the Y. Okay, so Y1, we will use red circles again. And we have 14, 2 2s, a 7, and a 0. Let's do some blue squares for Y2. A 10, a 3, 15, 7 5. It would be better if I was doing all the shapes the same size, but I'm doing my best. All right, finally, Y3 is yellow triangle. 6, 7, 12, 15, 15. All right, and I forgot to do the means at the same time. Remember, the means for the yellow triangle was 11. The mean for the blue square is 8. And then the mean for the red circle is 5. All right, now in the Y's, notice the data is all over the place. For instance, the range alone for the red circles, it ranges from 0 to 14. So it's all over the real number line. So compared to the first sample, the variability within each sample Y1 is big. So we're going to use these two separate hypothesis tests, these two separate ANOVAs, to ask ourselves this question. Which samples would more likely come from populations with the same mean? Okay, so here on the first example with the x's, the mean is probably most definitely somewhere around here. It's probably most definitely around 5. Likewise here, since it's really consistent, our samples are hovering around this 8. The mean from this population most likely is around 8. And here too, because all of the sample data is hovering around 11, the population mean is probably closer to 11. And now over here, we have the same space between the means, but the data is all over the place. So maybe this red circle at 5, it has a little bit more wiggle room because the data is all over the place. Likewise here, our data is all over the place again for the blue square. So the population mean might not be 8, it might be closer to 6, it might be closer to 10. There's more wiggle room because the variability within the sample is big. And the same argument for the triangle. So the Y's have more wiggle room because their data is all spread out. So for all we know, the means are actually the same. Let's write that down. So, well, we could just write the Y's more likely come from populations with the same mean. Okay, so moving on down, we call the variability among the sample means between sample variability. All right, so that's these guys, the means. And then we call the variability within the sample the within sample variability. Okay, and then those are the two things that we compare. So one way we compare them is by using a ratio. All right, so here's the argument that we were talking about before. If the between sample variability, so just to remind you, that was between the means, is large relative to the within sample variability, the x's, we have evidence to suggest the sample comes from populations with different means. So that was case X in that. All right, so variability among the means, there's definite space between the means, but within the sample, they all hovered around their own mean. So that would say, yes, the populations come from different means. All right, and then one way we do that is we make our ratio. And so this is going to end up being, our test statistic for our hypothesis test, and it's an F test statistic. So it's the between sample variability over within sample variability. Okay, so let's hop on into our ANOVA test now that we understand why we're using the variance to calculate the means. So here are our requirements. The populations are approximately normal, and you can use a normal probability plot for that. Populations have a common variance, and how we do that, and we'll talk about it later, or I can write it down now, but the largest sample standard deviation is no more than twice the smallest. And we could do that using a 1var stats. So the largest sample standard deviation, so we could just write something like SL, S is sample standard deviation, L is the largest, is no more than twice the smallest sample standard deviation. So something like that. All right, moving on, simple random samples. And samples are independent of each other. Okay, so independent sampling method. So let's look at an example now that we know the requirements, and we're going to calculate the F-test statistic by hand, of course, and then we'll see how to do it using our calculator. So the data in the table represent the number of corn plants in a randomly sampled rows for various types of plots. An agricultural researcher wants to know whether the mean number of plants for each plot type are equal. So there you go. All right, we have 1, 2, 3 populations. We see the populations right here: sludge plot, spring disc, no-till. Those represent 3 populations, and we're going to compare the mean number of plants for each plot. All right, if they're equal, the plot types don't really matter. If they're not equal, it means one outperforms the other. So an ANOVA test would be helpful for this farmer. So let's see how we're going to do this. First, let's state the requirements that must be satisfied. We just went over that. We don't have a normal probability plot, so let's just go ahead and assume it's normal. From a normal probability plot. Just to kind of get on with the show. Simple random sample. And then the rows are randomly sampled, and the also implies that the sampling method is independent. Okay? All right, and then the last one's a little bit weird. We want to make sure we have a common variance. And we said that means that the largest standard deviation, I'll write it in words this time, not symbols, is less than twice the smallest. Standard deviation. Okay, so that means that we're going to have to take all of our data and we're going to have to find the sample standard deviations for each plot type. Okay, so how do we find sample standard deviation? We do a 1-var stat. So we would have to put our information in L1, L2, L3, just like that. And we would then 1-var stats to get S, your sample standard deviation. And then you guys can pause and put all that into your calculator. And this is what we would get. So 1-var stats 3 times. S1 for the first plot is 2.80. S2 is 1.79. And S3 is 2.59. Okay, so which one's the largest and which one's the smallest? 2.8 is the largest, and so we want to make sure that it's less than twice the smallest, or 1.79. So is 2.8 less than 3.58? Yes. Okay, so those are the requirements. Let's look at our null and alternative hypothesis. It's always the same for an ANOVA. We have 3 populations. So, we would want our null hypothesis to look like this. Mean 1 is equal to mean 2 is equal to mean 3. And remember, the alternative, the mistake is to say not equal and not equal. But it's just that at least one is different. So at least one population mean number of plants is different. Okay. They don't talk about a level of significance, so we'll just do the standard 0.05. And now the moment has come to start calculating the test statistic. And it's a little bit involved, so we'll just do it by hand quickly. We won't get too bogged down in the calculations. And then we'll see how to use our calculator. So here we go. So the test statistic, again, is called an F-test statistic. First of all, we would have to take all of our plants and find the mean of all of the data. So we would have to put X1, X2, X3 maybe in another list, just one list, and run a 1var stats. And then you would see that the mean number of plants is 29.94 plants. Okay? And then going back, we would have to put, we did L1, L2, L3. We would actually have to go back and calculate the mean for each plot type using 1var stats again. Okay, so here's the mean number of plants for each plot type. Okay. In addition, we'd have to find the sample variance. We already found the standard deviation on the previous page, so we can just go back and square that to get the sample variance. Like that. Whoops. Okay, so now with all this information, we are going to calculate the between sample variability. And we call it the mean squared due to treatment, or the MST. It's essentially a weighted average of the difference of the sample means. And here's the other thing. It's an estimator of the variance, population variance, only if the null is true, that all the means are equal. Okay, so what does this look like? So the MST, it's a sum, and it's behaving like a weighted mean. Our sample size for each sample is 6. Oops. So we have 3 populations. We're going to do this 3 times. For instance, the mean of our first plot is 28.3. And we're going to see how much it differs from the overall mean, which was 29.494. And we're going to square it. And we're going to do that 3 times. So sample size is 6. And then 33 minus the overall mean. And we square it. Plus 6 times 28.5, running out of room, minus 29.04, and we square it. Sorry about that. And then we divide by k minus 1, and k is the amount of populations. So 3 minus 1. All right. And if you do that, we get that the MST, if you do that on our calculator, so the between sample variability is 42.3804. Okay. So we're going to compare the between sample variability to the within sample variability. And so this is the within sample variability. It's a weighted average of the sample standard deviations. It also estimates variance, which that happened up there too with the MST, whether the means are equal or not. Okay, so this one it estimates it no matter what. The MST estimates it only if the means are equal. So if the means in reality are actually equal, MST and MSE, what we're calculating right now, it should be almost the same. If the means really are equal, part D and part E are going to be the same. Okay, so with that, let's start doing this by hand. So it's a sum of n minus 1. N is 6, so 6 minus 1 is 5, times the variability, and it's a sum. All right, so we're plugging in all those numbers, and n minus k, well, it's the total n, not just in each sample. And so there was 3 samples of 6, so it's 18 plants altogether, minus our populations, which is 3. So throw that in our calculator, and we get 5.9174. All right, so those numbers look a little bit different. Okay, so now to compute the F-test statistic, remember it's a ratio. And it's the ratio of part D divided by part E. If the value is large, it means that those two vary. So if they're different, it means the sample means have to be different somewhere. Okay, so in our case, we had that 42.3804, and the MSE was 5.9174, and so we're looking at 7.162. Okay, so it looks like it varies, right? Now that we have our test statistic, this is normally where we would calculate where it was if it ends up being the critical region, we calculate that using the classical or the p-value approach. But that's even more tedious than actually calculating the test statistics. So we're just going to abandon ship, and we are going to bust out our calculator, and we're going to find the p-value using our calculator. Okay, so we'll finish up this section in our calculator video.